Welcome to section 10.2, Vectors in Space. We're going to revisit all the information we had discussed previously with two-dimensional vectors and apply it to three-dimensional vectors. Let's get started. Some things to review here is we know that a vector consists of a magnitude and a direction, and the vector is found using 2 points. We have our initial point and our terminal point. And remember, we're always going from our initial point towards our terminal point when we're talking about the direction of our vector. For our vector, we have to remember that our angled brackets represent a vector versus a point. And we have two general ways we can talk about a vector. The first way is component form, where we have the x, y, and now z values for our vector. So for our component form, it's going to be found by doing q1 minus p1, q2 minus p2, and then q3 minus p3. That's our third component this time. For the standard form, it's something we also reference as a linear combination. We're going to be incorporating the use of our unit vectors I, j, and a new one now, we have k. K is going to be a unit vector in the z direction. So you can see that if our component form was v1, v2, and v3, and we translate that to a standard form or a linear combination, we have v1 times I, because that's the unit vector in the I direction, or the x direction. And then we have plus v2 times j for a unit vector in the y direction. And then v3 times k, which is the unit vector in the z direction. For our first example here, we're going to go ahead and find the component form. Given the information, we know p is the vector 3, 4, 2, and q is going to be the vector 3, 6, 4. If I want to find the component form of the vector between those two, what I'm going to do is subtract components. Remember that p is our initial point, q is our terminal point, so it's always going to be q minus p based off how it's listed. So using my formula, I can go ahead and do q1 minus p1, q2 minus p2, q3 minus p3, and I get my final vector of 0, 2, 2. If I want to take that component form of a vector and translate it into a standard form, I'm going to pick out each component and give it the correct unit vector. So again, we're going to be adding an I, a j, and a k. We add I to our v1, j to our v2, and k to our v3. And I now get the vector 0i plus 2j plus 2k. It's not necessary to put the 0i there. I could have just said 2j plus 2k, but I wanted to put it there just to show that that's what the I would be attached to. So if you're dealing with something and it's missing an I, a j, or a k, in the component form, we would represent that with a 0. And it's perfectly acceptable to put a 0 next to a unit vector to represent what would be there if there was a value. For our scalar multiples, we're going to operate the same way they did as our two-dimensional vectors. I'm going to take whatever my scalar value is, in this case it's k, and multiply by each component of my vector. So I have a times v1, a times v2, and a times v3. Building off of our scalar values, we talked about the idea of being parallel, and two vectors are parallel if one is a scalar multiple of the other. So if I have vectors u and v, and I could say for certainty that u is equal to 2 times vector v, then they are different by a scalar value of 2, which means they are in fact parallel. It could also be a fraction. I could say maybe u is equal to 1/3 of v. That 1/3 is still a scalar, so these vectors would still be parallel. And I could even add in a negative sign if I wanted to. My scalar here would be a negative 1/3, but they are still related by a scalar value, so they would still be parallel. For our examples here, I have u and v as the vectors 3, 2, 1, 4, negative 1, and 5. We'd like to find 3u and also 4v. So I'm going to take my scalar and multiply by each component of the given vector. In order to find 3u, I'd multiply 3 by each component. And if we do that successfully, then we're going to get 9, 6, and 3. I'm going to do a similar action to find 4 times v. I'll take each one of my components and multiply them by 4. So again, doing that successfully would give me the vector 16, negative 4, and 20. A new concept we now have is the idea of collinear points. So 3 points are collinear if the two vectors they create are parallel. We're going to explore this concept with the 3 points 2, negative 1, 4, 5, 4, 6, and then negative 4, negative 11, and 0. The first thing we want to do is we want to find two vectors. So I'm going to find the vectors PQ and PR. For vector PQ, we're going to do Q minus P to find our vector. So we have 5 minus 2, which is 3. 4 minus a negative 1 is 5. And 6 minus 4 is 2. For vector PR, we have negative 4 minus 2, which is negative 6. Negative 11 minus a negative 1, which is negative 10. and then 0 minus 4, which is negative 4. So now what we're looking for is there a number where I can multiply each component of PQ and turn it into a component of PR. So what I'm going to do here is take components from PR and divide them by components from PQ and see if we get a constant ratio here. We can do negative 6 over 3, and we get negative 2. I can also do negative 10 over 5, and again, I get negative 2. And then last but not least, I can do negative 4 over 2, and I get negative 2 again. So since there is a scalar multiple, in this case negative 2, that I can multiply one of my vectors by to get the other vector, that means that these 3 points must be collinear. One thing that's very important to note here too is when I made my vectors, I had P, Q, and PR. So each one of my vectors had the same initial point. That's very important when you're constructing your vectors here. For our magnitude, just like the other formulas, it remains the same except we're adding on an extra component here. So I have my x component squared, my y component squared, and now my z component squared. We'll add them all together and then take the square root. For our example here, we're going to go ahead and use the vector 3, 6, 4. I'm going to plug the components into my equation here to find the magnitude. And when I do that, we get 3 squared plus 6 squared plus 4 squared. I'm going to go ahead and square everything and add it together, and I get the square root of 61, and that's my magnitude. For our next example here, we have the vector 3, 4, 2. We're going to do the same thing and plug in our components into our magnitude formula here. So we get 3 squared plus 4 squared plus 6 squared, and then when I simplify all of that, I get the square root of 29. If we want to take a vector and convert it into our unit vector, again, we have another similar formula. We take our vector itself and we divide it by its own magnitude. And we can do it in any of our equation like this, or we can do each component over the magnitude. And we had one other alternate form from 6.3 you can use as well. As an example of finding our unit vector, we're going to start with the vector 0, 2, 2. Again, the first task is to go ahead and find the magnitude for a vector. So we're going to go ahead and square each component, plug it into our formula for the magnitude, and we end up getting the square root of 8. And then if we simplify that, that becomes 2 radical 2. So if I now take this and I plug it into my unit vector formula, what we end up getting is our vector 0, 2, 2 divided by its own magnitude. And if we wanted to go ahead and space it out a little bit, we could take each component and divide it by the magnitude. So I would have 0, 1 over radical 2, and then 1 over radical 2 as a different form of my unit vector. For our dot product, as our example for finding the dot product, we're going to use our vectors 3, 4, 2 and 3, 6, 4. Again, looking at our formula, we're going to multiply together common components. So my U1 and my V1, my U2, my V2, and then my U3 and V3. I'm going to go ahead and plug those into my formula. So we get 3 times 3 plus 4 times 6 plus 4 times 2. Again, just pulling out our common components from our vectors. When I go ahead and simplify that, I do in fact get a scalar, which is 41. So I know my answer is on the right track. And for our final formula today, we're going to be finding the angle between two vectors. So that's going to be the cosine of u is equal to the dot product of u and v divided by the product of the magnitude of u times the magnitude of v. And just to note, even though our formula says cosine of theta equals, there is one last step. You would have to take the cosine inverse of both sides to turn it into your actual angle. Let's go ahead and take a look at this. So we're going to go ahead and use the vectors we've been working with, vector u and vector v. Conveniently, throughout this whole lesson, we've already found the dot product and we found the two magnitudes of each one. We're going to take those values and plug them into our equation, and then we're going to go ahead and take the cosine inverse of that ratio to turn it into our angle. All right, so again, using those same vectors, we're going to find the dot product first. So the dot product of u and v is going to equal 41. Again, we've already found that. Then we want to find the magnitudes. So the magnitude of u we found to be radical 29, and the magnitude of v we found to be radical 61. We can go ahead and plug those values directly into our equation here, and we get the cosine of theta is equal to 41 over radical 29 times radical 61. If I go ahead and then take the inverse of that fraction, I can get an expression for my angle, and then by plugging it into the calculator, we should all get the angle of 12.88 degrees. All right, that does it for our lesson today. Go ahead and get started with the homework, and good luck.